Now that we know some strategies for solving quadratic equations, let's try to solve some quadratic applications. Remember, I like to always say that math doesn't live in a vacuum, and we want to actually take these skills and apply them to some real life problems. The strategies that we're going to follow are the same that we followed for linear equations, where we want to read the whole problem first. If you can draw a picture, absolutely do so. Write out the equation next, and make sure in the end to check your answer and make sure that it makes sense with the actual problem that you were asked. We're going to again today see some formulas that are going to look familiar, maybe from geometry, or maybe if you've taken physics, they'll look familiar. The equations are not everything, but they are a good starting point a lot of times. Question 1, example 1. A trough at the end of a gutter spout is meant to direct water away from a house. The homeowners make a trough from a rectangular piece of aluminum. So we know we have a rectangle. The rectangular piece of aluminum is 20 inches long and 12 inches wide. They make a fold along the two sides. They make a fold along the two long sides. So they make a fold along this side and along this side. And it says that fold is a distance of x inches from the edge. So this length is x and this length is x. If they want the trough to hold 360 inches cubed of water, that's a volume. If you see a length measurement cubed, that makes a volume. So they're making a cube out of this thing that's going to hold water. How far from the edge must they make the fold? So we want to know what x is here. If we want the volume, then we need length times width times height. Here, it's easy to say that 20 is the length, but what's the width and what's the height? So if this whole thing here is 12, then this part, the actual length, after we take these wings and fold them up, is going to be 12 minus 2x, right? It's 12 minus that x. And the height, once we fold this up, the height is going to be that x. We could sub those into our formula for length, width, and height. Once you sub it in, I like to distribute from left to right, so I'll distribute the 20 in first. Then I'll distribute the x into all those things. Trying to get all the variables to one side and equal to 0 so we can use any of those strategies that we used last class. Remember, it has to be equal to 0 to solve by factoring. It has to be equal to 0 to solve with the quadratic formula. And here I chose to move things to the left because that will make our x squared a positive number. Once you get to that point, you can notice that everything is divisible by 40, and you can divide everything by 40 to make your life simpler. If you don't do that, you can still factor it just the way it is and get the correct answer. That has 3 terms, so you can factor it using star method. That breaks down into x minus 3 and x minus 3. And so our two solutions should be 3 and 3. That means x must be 3 inches. That does make sense with our problem because we know it must be much smaller than that 12 and the 20. Sometimes it gives you the picture with the problem. Sometimes it does, sometimes it does not. A box is going to be formed by taking a sheet of cardboard and cutting away 2 by 2 inch squares. So here you see I've marked out, they're cutting out this square, cutting out this square. They're cutting out every single corner square here. They want to form a box in the end that holds 56 inches cubed. Cubic, that means volume. Again, I have volume equals length times width times height because we're dealing with a rectangular prism. The length of the original piece of cardboard is 3 inches more than the width. That's where they got the x plus 3 and the x. We're going to have to do a little bit more fidgeting here, though. So if our total here is x plus 3, and we're taking out 2 here and 2 here, then this length right here must be x plus 3 minus 2 minus 2, which would be the same as x plus 3 minus 4, which is the same as x minus 1 if you go through and simplify that. Similarly, this length right here is x, right? This whole x minus 2 minus 2, or in other words, x minus 4. And then our height, if we could picture this, they're going to take each of these and fold them up to make that box. They're going to take these wings and fold them up to make that box. And the height is going to be right there, that 2, right? Or that 2. Either way, the height is 2. We can sub those in for our length, width, and height. Again, I like to distribute left to right, so I'm going to FOIL those two binomials together. Then that 2 is still out on the side, so I'm going to distribute the 2 in. To try and get it equal to 0, we can subtract 56 from both sides. That gives you something like this. Again, you can factor from this step, or you can notice that you could take a 2 out of everything. Once you take the 2 out of everything, you could do the star method. That gives you x minus 8 and x plus 3. So we're trying to make each of those parentheses 0 based on that 0 product principle. X must be 8 and negative 3. That's what x is, and remember x is our width here. Which one of those makes sense, we have to ask ourselves. Certainly not the negative 3, right? The negative 3 does not make sense because we can't have a side of a box be negative 3 inches. So then if x is 8 and our length is x plus 3, then it must be 11. All right, this one again, it gives us a picture. A window's in the shape of a rectangle. It has a right triangle above it. The length of one leg of the right triangle is 2 feet less than the hypotenuse. So we call our hypotenuse x. The length of one leg is 2 feet less than that. It must be x minus 2. The other leg is 1 foot less than that. It must be x minus 1. It doesn't matter which one we label, x minus 1 and x minus 2, as long as our hypotenuse is the biggest side. And when we go to do the Pythagorean theorem, right, anytime we have a right triangle, we could do the Pythagorean theorem. Anytime we do the Pythagorean theorem, the c has to be the hypotenuse. That's the longest side, the diagonal side of the triangle. So that c is going to have to be x. It doesn't matter, the a and the b are interchangeable. When I sub a and b into that formula, and c in for x in for c, this is what my formula looks like. Whenever I'm squaring a binomial like that, I prefer to write it out twice. It helps to look at it. You can distribute the x minus 1 to x minus 1, distribute the x minus 2 to the x minus 2. Again, combine like terms on the left. Subtract the x squared over to try and get it equal to 0. We could do star method to factor it because it has 3 terms. And then to solve it, x must be 5 and 1. We need to figure out which of those answers makes sense. If we had x equals 1, then this side would be negative 1, and this side would be 0. So 1 does not make sense, but 5 does. If we want to know the lengths of all the sides, if x is 5, this one must be 5 minus 1 would be 4, and this must be 5 minus 2 would be 3. So our 3 sides of our triangle are 3, 4, and 5. Another right triangle. If we have a right triangle, odds are we're probably going to use that Pythagorean theorem. It sets us up here with a hypotenuse of 10, each leg being x and x minus 2. The only thing that matters is that the c is 10, the hypotenuse is 10. The other two are interchangeable. So our formula when we plug in our values should look like this. Again, we could square each of those and distribute, combine like terms, and solve. We're thinking about sides of a triangle. So if we're talking about which one of those makes sense and which one doesn't, the negative 8 does not make sense here for a side of a triangle. The 6 does. Since 6 is x, if we want to find the other side of the triangle, we could say x minus 2, or 6 minus 2 would be 4. All right, this is another formula that's given to us here. It's the height of an object based on the time that the object's been in the air. This is any object that's been tossed or dropped or anything like that. It's an object in free fall. It gives us all the values for the variables that go with it as well. So here's the formula, right? It has a lot of variables in there. The values for the variables, or the type of those variables, are listed here on the left. G is the acceleration, and G really depends on what type of values you're given in the problem. So if in your problem you're given feet, you're going to go with 32. Feet squared, feet per second, you're going to go with 32. If in your problem you're given meters per second, meters squared, you're going to go with G equals 9.8. Those are your 2 different values of G that you can use. One of them you'll use if you're using metrics units. The other you're using if you're using standard English units. All right, for example, it says if the initial height is here, the initial velocity is here, gravity is this, we can sub in those values to the formula, and that is our position based on the time. Now, if it told us it was in the air for t equals 3 seconds, all we would have to do is sub in a 3, and it would tell us the position. Vice versa, if we know that the position is 20 feet, we could sub in 20 for s and try and solve for t. Here's an example of that. A model rocket is shot straight upward from a launch pad 1 meter above ground level with an initial velocity of 24 meters per second. If you go back and look at that past page, you could start to label things. So I've got my 1 meter labeled as S naught, that's the initial position. 24 meters per second labeled as V naught, that's our initial velocity. Since we're dealing in meters, our A is going to be 9.8 meters per second squared. The formula never changes, so now all we have to do is start to sub things into that formula and simplify. If for part B we want to find the time at which a rocket is at a height of 20, we know that S is our height, so we can sub a 20 in for S. Move the 20 over to the right and use the quadratic formula to solve will give us two answers, 3.9 and 1.0 seconds. We have two times where it's at 20 meters. It's because if we launch something, it's going like this, right? So it's at 20 meters here, and it's at 20 meters here. It hits that twice at two different times, at 1 second and then almost at 4 seconds. Here's another very similar to that. A fireworks mortar is launched straight upward from a pool deck, 2 meters off the ground. That's our initial height. With an initial velocity of 40 meters per second, that's our initial velocity. Write a model. Look, this is in meters. We know that our acceleration is going to be 9.8 meters per second, right? Meters per second squared, since we're dealing in meters. Write a model to express the height. Sub in the values that we have and simplify. Find the time at which the mortar is at a height of 60 meters. So if the mortar is at a height of 60 meters, that's our height. We want to solve for time. We can sub 60 in for S. Subtract 60 from both sides. Simplify. Use the quadratic formula. And again, we get 2 times, again, because we're launching a mortar, and it may be here and here. At 2 different times, it's at that specific height. These are not all of the types of quadratic applications, but it is a good variety of quadratic applications that we've seen today. You may see other ones, but the strategy still holds that you want to, if you can, draw a picture, write out a formula, use some geometry formulas, solve, and then make sure that your answers actually make sense with the problem.